We're going to continue with our lessons on gases. This is the third of 4. We'll finish up tomorrow. Remember, quiz on Thursday, big fat test on Monday, but you'll be well prepared, so we won't worry. What we're going to start off with today is where we left off last time. We're just going to take it a step farther. So for example, which gas law is this? Ideal gas law. And what we want to do is link the ideal gas law with stoichiometry. This is all going to fit into big idea predominantly 2, but we're going to explore big idea 2 in a lot more detail in the second 9 weeks. If, for example, you're given the mass of a solid or a liquid and you want to know the volume or pressure of a gas, gas laws are for gases only. So you can't put information about the mass of a solid or a liquid into a gas law. You would need to do a conversion from the mass of a solid or a liquid to moles of gas, and then you could use the ideal gas law. Another thing we're going to look at is the link between the combined gas law and volume stoichiometry. The combined gas law is for the same gas under different pressure and temperature situations. So if you are ever given information about 2 different gases under different sets of conditions, you will need both volume stoich and the combined gas law, and we'll walk through that. You should have seen this in honors. It should be review. If it's not a big deal. It's pretty easy. We'll walk through the first example together, and then you'll have a shot at one on your own. There are more problems like this at the end of the chapter in your textbook, and again on the course outline, which is in the first day handouts tab on Edline, you will find a listing of recommended problems for each chapter. The only way to get good at anything at chemistry is to do a lot of practice, so I'd certainly recommend those. In your notes, what you've got here is basically everything I've just said. First thing we're going to do is look at the combined gas law in reaction stoichiometry. In this first example, we've got propane and oxygen gas. Propane is what you attach to your grills, reacting at a temperature of 27 degrees Celsius and a pressure of 1 atmosphere. If 0.5 liters of propane react with an excess of oxygen, we want to know what volume of CO2 should be generated at a different temperature and pressure. So the key that this is not simply a combined gas law problem is you're given information about one gas, but asked for information about a different gas, and that's why you cannot use the combined gas law right away. So what you need to do here is first find the volume of CO2, first find the volume of CO2 under the first set of conditions. So let's get everything down and remind ourselves how to process this type of problem. So we've got propane reacting with oxygen gas, yielding CO2 and water. You should be able to balance chemical equations with ease. That's something you mastered at the honors level. I like to write the information about the substances directly under them. I think it's easier. The volume of propane is 0.500 liters, and the temperature is 27 degrees Celsius or 300 Kelvin. The pressure is 1 atmosphere. We want to know the volume of CO2. The temperature here is 310 Kelvin, and the pressure is 1.50 atmospheres. So again, at first glance, this may look like a combined gas law problem. However, thank you. However, you've got two different temperatures and pressures for different gases. So this requires volume Stoich, then the combined gas law. What you first need to do is get the volume of CO2 under this set of conditions. So you have 0.500 liters of propane, and you want to get the volume of CO2 under this set of conditions. Volume stoichiometry is under one set of conditions. From the balanced equation, as we mentioned the other day, instead of mole ratios, you can have volume ratios for gases. And 3 times a half is 1.50 liters of CO2. That is V1, the volume under the first set of conditions. Once we have that, we want to get V2, the volume of CO2, under the second set of conditions. So again, if you are given information about two different gases, you must first get to the other gas under the first set of conditions doing volume Stoich, then you can do your combined gas law. So we have P1 V1 over T1 is equal to P2 V2 over T2. We want V2, and again, variable manipulation at this level should be second nature. You should not have an issue moving variables in an equation. V2 is going to be T2 times P1, and this is the beauty of labeling everything. It's right there for you. It shouldn't be an issue. Now be careful with V1. It's the one you worked hard to get through volume ratio. P2 is 1.50 atmospheres, and T1 is 300 Kelvin. And you actually can see this is slightly greater than 1. If you didn't have a calculator, you can see how those numbers actually cancel. And then you're going to have about 310 over 300. So it's going to be just greater than 1. And you get 1.03 liters rather. Volume is going to be 1.03 liters, the volume of CO2 under the second set of conditions. Yes. Yeah. Alrighty. Easy?
What was the point of doing the stoichiometry?
The point of doing the stoichiometry is you first had to find the volume of CO2 under the first set of conditions, because you cannot put information about different gases into the combined gas law. And the information you were initially given was on propane for its volume.
Okay.
All right? The second problem is very similar, although it has a limiting reagent aspect to it. So give that one a shot. See if you can do that, and then if you need more, you're going to find plenty of them, and you will need more in your homework. Big or little?
Like normal size? Yeah. Thank you.
All right, so give this second one a shot. Are you done? Just kidding. You have to write and balance the equation and figure out the limiting reagent. At the top of the screen. This is a combustion reaction, right? Did we balance the equation?
Yeah.
What's the coefficient of oxygen? 15. Okay. Did you get the limiting reagent? What's the limiting reagent?
How can you tell? Because we only have one volume.
They gave you 2.
Oxygen? Oh. Yeah.
So you have the balanced equation correct? Yes? They gave you the volume of pentene and the volume of oxygen. And why is oxygen limiting here?
Well.
So this is 5 times this, right? That's what you're given. But the need is 7.5 times. So you don't have, or you're not given as much as you truly need. If you don't understand that concept, you can divide each of them by their coefficient, and you'll see clearly that oxygen is limiting. So at this point, you're where we were previously. So what do you need to do?
You take the 2 liters and like multiply, like use stoichiometry.
Almost. Why do you take the 10 liters of
Oh,
O2?
the limiting.
Because it's limiting. The limiting always determines how much reagent reacts with it or it generates. So from the 10 liters of oxygen gas, you're going to get the volume of CO2 under this first set of conditions. So did you get 6.67 liters of CO2 as the volume under the first set of conditions? Is this your V1? Is that what you got? Okay, and once you get that, what do you do next? Combine gas law. So once you have the volume of CO2 under the first set of conditions, which you get by volume Stoich, this is your volume Stoich right here. Then you should have gotten a volume of CO2 under the second set of conditions is 2.30 liters. Is that what you got? All right. And that's an honors level question. That's something that you should have done in honors. We certainly did. very evident to me that you need more practice here, and those homework problems at the end of the chapter that correspond will be very helpful to you and should be done for tomorrow. You should understand everything we've discussed through today by tomorrow if you want to have a greater chance of success on your quiz. All right, so we can link volume stoichiometry to the combined gas law. That one sometimes is a little bit tricky to recognize, but usually what is very easy to recognize is the link between the ideal gas law and stoichiometry. And again, if you're given the mass of a solid or a liquid, you can calculate a variable about gases, but first you have to do stoichiometry in order to get moles of gas. So in this example here, it says quicklime, which is calcium oxide, is used in construction. And the way that it's manufactured is by decomposing calcium carbonate. This is a decomposition reaction like we talked about earlier in the year. You should be comfortable with decomposition reactions in terms of predicting products. We're going to use this reaction now to process the following problem, and I think this will be pretty straightforward to you. You want to know the volume of CO2. The temperature is 825 degrees. That's very high. That's what it takes to decompose calcium carbonate. The pressure is 0.992 atmospheres, and you're given a mass of solid. How would you go about doing this problem? Let's get the information down and see if you can figure out how to drive it. So what we've got here is calcium carbonate. We're going to make calcium oxide and CO2. And we talked about metallic carbonates generating metallic oxides and CO2. We want to know the volume of CO2 in liters. The temperature is 825 degrees Celsius. I believe that's 1098 Kelvin. The pressure is 0.992 atmospheres. And the mass of the calcium carbonate is 45.8 grams of that substance. Now, gas laws are for what state of matter only? Gases. And they gave you information on a solid. So what do you need to do before you can do the ideal gas law? Faith?
Can you use stoichiometry to convert the grams to moles and then moles to a gas?
Exactly. So what you want to do is you want to convert the mass of the solid to moles of solid. That'll be our N. You want to get moles of CO2. So 1 mole of calcium carbonate is 100.09 grams of it. And then 1 mole of calcium carbonate is 1 mole of CO2. And we have 0.458 moles. That's the N. Now you want to get the volume. You have PV equals nRT. To solve for volume, we're going to divide both sides by P. We've got 0.458 moles. The pressure's in atmosphere, so 0.0821 liters atmosphere over mole Kelvin. That is a constant that's provided to you. They may give you 0.08206. They're both going to come out the same, don't worry. The temperature is very high at 1098 Kelvin. And we're going to divide by the pressure. And that will be the volume of the gas. The key here, there's nothing here that's difficult. You just have to recognize when to do these steps. And again, gas laws are for gases only. Okay? Not difficult. The other problem that's similar to this, I would like you to star, and I want it done for tomorrow. You can work on it at home. It's grossly similar to what you were just given. The other crux today is going to be on partial pressure, which we did last year. Pretty straightforward. Probably going to do a little more complicated work with it. And we're going to work on this stopcock closed and open problem. If you spend some time on the POGO packet that was on partial pressures, your level of understanding of this section is going to be very high. The POGO packets are really important because they provide you with diagrams, but more than that, they make you think. So by spending the time there, you will understand the concept a lot better than anything you're going to get in class or from your textbook. The other packet I gave you is on the Maxwell-Boltzmann constant concept. And that's something, if you haven't looked at already, I highly recommend that you go through it prior to tomorrow's class. That is a new concept, and when I initially saw it, I couldn't imagine why that was part of the curriculum. But after working through the POGO packet, I really felt that it made sense, so I would highly recommend that packet. In regard to Dalton's law of partial pressure, let's really try and simplify it, similar to the way we did last year, and then we'll get into collecting water over gases like you'll do in the lab tomorrow. I was just setting that up for you. So for example, you can have any type of collection apparatus. Let's say you had this one, and we want to put a rubber stopper in it so we don't lose any gas. For example, let's say that the orange circles represent oxygen gas, and let's say that the green circles represent, I'm going to use a noble gas because I don't want them reacting with one another, helium. The gases move in a straight line fashion, colliding with the walls of the container and sometimes with one another, but they're not attracted to one another in any regard under ideal conditions. When the molecules move around and collide with the walls of the container, they will exert pressure on the walls of the container. And when you have a mixture of gases, the total pressure that all the gases exert is equal to the sum of the partial pressures. This is known as Dalton's law of partial pressure. So the total pressure is equal to the sum of the partial pressure of oxygen plus the partial pressure of helium. The more moles of gas you have, the greater the pressure exerted on the walls of the container. So this would be the partial pressure of helium gas. We also know, for example, that we can get pressure by doing pressure times volume is equal to moles times the universal gas constant times T. So if I want pressure, that's equal to nRT over V. Now if I only want the pressure of the helium gas, I only take into account moles of the helium. If I want the total pressure of the gas, then I would have the total moles times R times T over V. So if I only wanted it for O2, I'd only have moles of O2 there. Same thing for helium. Keep that in mind as we work through this example. And this example has numerous parts to it, but we're going to take it one step at a time. This is known as Dalton's law of partial pressure. The total pressure that the gases exert is equal to the sum of the partial pressures. Okay? Now, if the gases were to react with one another, it's a little more involved, and that's why I picked a noble gas to keep it simple. I want to show you in this example how you can really start mathy and get conceptual. It says a 1 liter sample of dry air. So the volume is 1 liter. At 25 degrees Celsius, so 298 Kelvin. Contains, we've got moles of nitrogen gas at 0.300. We've got moles of oxygen gas at 0.600. We've got moles of argon at 0.400. And we have moles of carbon dioxide at 0.200. We want to calculate the partial pressure of oxygen gas. We want to calculate the total pressure. We want to compare the partial pressure of nitrogen versus that of oxygen, and we want to explain how and why they differ. First thing we want to know is the partial pressure of oxygen gas. How will we get that?
Is the ideal gas law with the mass of oxygen?
Almost, not the mass, but the moles, because they gave you moles, so you wouldn't want to switch to mass. It'd be work you don't need to do. Moles of O2, RT over V. So we've got 0.600 moles, 0.0821 liters atmosphere over mole Kelvin. I just decided to go in atmosphere because it's easy. 298 Kelvin divided by a volume of 1 liter. And so the partial pressure of oxygen is 14.7 liters, although in terms of sig figs, this was initially in 2, so let's just say 15 liters. Make life easier anyway. next question was to get the total pressure. How are we going to get the total pressure? And think simple. All right, so if we add up all the moles, we get 1.500 moles. You got it. So instead of this, we would have put this in. Now instead of replugging all of that, if you do 1.5 divided by 0.6, you get 2.5, right? So it's 2.5 times what you had. Does that make sense? So the total pressure, you have 2.5 times the moles of oxygen gas. So the total pressure is 2.5 times that, which is 38 liters. Alternatively, you can do this times this over that. But I know this over this is 2.5. So 2.5 times what I had here will give me this pressure.
But why did you divide by 0.6?
What did I do what?
Why did you divide by 0.6?
I just wanted to figure out what the multiple was. If you're 16 and I'm 32, how many times older am I than you? 2. Same concept. So the total moles is 1.5, but this was this, so this over this tells me how many times more the total pressure will be compared to that one. Light bulb. Yep, you got it.
Okay.
All right? But my 32 example made me feel good, so 32, the good old days. All righty. Next question. Compare the pressure of nitrogen gas with the pressure of oxygen gas. I don't want to do all this work again. What could I do?
Take the 38 liters.
Could you find the same ratios?
Yeah.
Exactly. Work on the ratio aspect. So how many times more is oxygen gas than nitrogen in regard to moles?
Twice as
Well, let's do
much.
it the other way. We had oxygen, and nitrogen is half of this. So that means the pressure of the nitrogen gas has to be half of that of oxygen. So what you can see then is that the more moles of gas you have, the greater the pressure, because moles and pressure are directly related. And you want to understand the relationship between variables in any equation. So if you look at this, you can see that pressure and temperature are directly related. Volume and temperature are directly related. Pressure and moles are directly related. Volume and moles are directly related. What's the relationship between pressure and volume? Inversely related. Okay? You can get sneaky with it too, because you know, for example, that pressure times molar mass is equal to the density, which is mass over volume, RT. So again, pressure and volume are inversely related. Molar mass and volume are inversely related, etc. So be comfortable with that type of relationship. Okay? The last problem I want to show you is something new. It looks very hard, but you're going to find it extremely easy because you are very good at concepts and even better at math. So the last thing I want to show you is this type of problem, and you'll find a few in your textbook. I recommend them all. It says 2 flasks are connected by a stopcock as shown. When the stopcock is closed, an unknown alkane is in a 5-liter vessel on this side, at a pressure of 2 atmospheres. Propane is on this side. It occupies 2.5 liters of space and it exerts a pressure of 0.75 atmospheres. I can calculate the total pressure of the system when the stopcock is open, because what's going to happen when the stopcock is open? The gases are going to move down their concentration gradient from high to low, and they're going to mix. And together they will exert pressure on the walls of the container. What will be the volume of the vessel when the stopcock is opened? 7.5 liters. You just add the two. The approach to doing this type of problem is pretty straightforward. You want to calculate the total volume when the stopcock is opened. That's equal to 7.5 liters. Calculate the pressure of each gas with an open stopcock and then add the two together. Let's take a look and you'll see this is pretty straightforward. I've got an unknown alkane on this side. The volume is 5 liters. The pressure is 2 atmospheres. I've got propane on this side. The volume is 2.5 liters and the pressure is 0.75 atmospheres. The total volume when the stopcock is opened is 7.5 liters. How would you propose that we calculate the pressure of the unknown alkane in the open position? What's Boyle's law? P1 times V1 is equal to P2 times V2. Well, what if these are the ones essentially in the closed position, and what if this becomes the twos in the open position? So what you've got here, instead of P1 and P2 or V whatever, maybe it's closed and closed, and VT is essentially VO and PO. So you've got pressure in the closed times volume in the closed is equal to pressure in the open times volume in the open. And to solve for pressure in the open position, you're just going to divide that product by volume in the open position. So what you've got then for pressure in the open position, you've got 2 atmospheres times 5 liters over 7.5 liters, and without a calculator, you've got 10 divided by 7.5, which is 4/3, or 1.3 liters.
Could you do it with the other ones too?
Yeah, so now you're going to do it with this one. How would you get pressure in the open position for these guys? Same formula. Pressure in the closed position is 0.75 atmospheres. Volume in the closed position is 2.5 liters. Volume in the open position is 7.5 liters. And again, without a calculator, 0.75 over 7.5 is 0.1 times 2.5 is going to be 0.25 liters. How will we get the total? You know, I'm so stupid. Look what I did here. This isn't liters. What unit is this, dum-dum? I'm the dum-dum. Atmosphere. And this is also, right? That's bad. Cancel your units so you don't make ding-dong mistakes. Oops. So what's the pressure total. How do we get that? You add it together, and you're maintaining one decimal place, so it's 1.6 atmospheres. I'm sorry I tried to rush, but we still have a few minutes. So again, find pressure in the open position for each one. Add the two pressures together. They, of course, have a unit of atmospheres, and you get 1.6 atmospheres. We'll pick up next time. Really important that you have a solid beat on everything we've done so far. And if you can at least preview the Maxwell-Boltzmann constant packet, it's going to help you a lot. Next time, to finish up this concept, we'll be linking mole fraction to partial pressure. Very, very easy. Molecular reps, also very, very simple. And we'll get into the Maxwell-Boltzmann distribution as well as diffusion and effusion, most of which you saw last year. I also want to take the time to show you how you did on your test and where you stand right now.